Hi, everyone. I'm Ryan Craven from the Office of Naval Research and the DoD, and I'm one of the program officers that manages the Cybersecurity and Complex Software Systems program at ONR. So I've been at ONR about 5 years now, and I've been a civilian with the Navy for about over 15 years. And it's really a pleasure to speak to you today about the kind of work we do and hopefully give some context to set the stage for what will hopefully be a great discussion to follow. So for anyone who's not familiar with our command, I'd just like to give a quick word about our organization and our role in bringing new technology to the naval forces. So the Office of Naval Research is located in Arlington, Virginia, and we serve as the headquarters activity for science and technology research in the Department of the Navy. So that means we direct or oversee pretty much all of the basic and applied science and technology efforts for the United States Navy and Marine Corps. And we work with partners from around the naval community to define research strategy, and then to both plan and direct those subsequent research efforts to accomplish that strategy. So in the course of doing this work, we work closely with a variety of partners from across academia, industry, national labs, and really all of the naval labs and warfare centers that you see here on the map. If you look kind of in the middle of the right column, you'll see the Office of Naval Research in Arlington. And so we partner with a lot of organizations, both domestically and internationally, to advance research that can benefit the mission of the Navy and Marine Corps. So that's kind of what we do at a high level at ONR. In our group specifically, we're focused on cybersecurity research. So we do a lot of work in system security, dealing with various cyber challenges, right? Challenges why we're here. Basically, cyber exploits just keep coming and coming, right? Ultimately, it's very easy to find a vulnerability in a piece of software, but it's the hardest of hard problems to actually say that a piece of software has no vulnerabilities. So there's really a lot of challenges here. There's just this constant supply, what you see in the community, this constant stream of new 0 days or new vulnerabilities being discovered. And it's really, all of the software we use across all of our systems is really just full of these ticking time bombs that are waiting to be discovered and used by attackers. And you see it in kind of the slide here is a couple of different areas to highlight. So you see it in various things like competitions that take place. So here's a blurb about an own competition. This is a typical like an annual competition that takes place where the organizers basically buy bugs from people that they discover new bugs, new vulnerabilities in popular software during this event. And usually it's very successful. A few years ago, I think they found 51 new 0 days over the course of a weekend and spent about $833K buying these bugs. And oftentimes when you look at these events, it's not, really obscure software being broken. It's very popular things like, Microsoft Edge was new at the time and it had been broken that year. VMware, even without the guest tools being installed, getting a VM jailbreak. So there's really a lot of, big serious bugs that get found there and fixed early, which is really nice that, they get responsibly disclosed so they can be fixed. But that's not always the case. So you see other instances where, like at the very bottom left is, there's entire 0 day marketplaces out there on the internet. This is an image from one called Zerodium. You actually go to their website and they will list out, graphically what they'll pay for 0 days to different popular pieces of software. So like for instance, if you can come up with a remote code exploit for iOS, they'll pay, write you a check for probably millions of dollars. It's really a point of frustration. Oftentimes we find that these bugs are showing up in code that we don't even need in a lot of cases, right? So good examples of that a few years ago was this vulnerability called Heartbleed. A lot of you probably saw it. It got a lot of press at the time. And it turned out it was actually it was in a functionality of TLS that was called its heartbeat feature. And really a lot of servers weren't even using this, but it was there. It was part of the software, part of the code, and it could be triggered by an attacker to leak memory out of a server. So really, really serious stuff. And it's happening all the time and constantly. What's also really scary is that it happens in stuff that we've been using for a long time. So last summer, there was a group of bugs called the Urgent 11 vulnerabilities, and these were some pretty serious bugs in VxWorks. And for those that don't know, VxWorks is a really important operating system, right? Because it powers a lot of critical real-time systems, things like weapon systems and a lot of embedded, real-time systems. And these bugs went back over 15 years of releases. They had been there for a decade and a half, basically. And so how do we get our hands around this, right? The timelines are shrinking. We're seeing now where vulnerabilities get disclosed on the internet, and then various APT groups are using them within hours. And so, especially when we talk about the gaining the ability to be able to automate finding new vulnerabilities, that timeline is going to be shrinking even more. So, how to be proactive and get ahead of this problem is a big area. This begs the question: what do we do about it, right? At ONR, we've really tried to narrow the focus and find a clear path forward that works for us to help meet naval needs. And that's really important to us, right, as we're a mission-driven organization. So for this intro today, I'm just going to touch on a few different research areas within ONR where we're working, and really try to pull them around a common theme that I want to advocate for. And that is this idea of legacy systems. Naval platforms especially have exceedingly long lifespans. When you compare them to average things that maybe get used for 10 years, naval platforms can get used for 30, 40, 50 years. And so there's a big, broad variety of code and hardware and software systems of the different ages and longevity across these systems, right? What we try to advocate for within our program is to be able to work with what we've got. So if you look at a lot of research across the community, there's always a tendency to make these assumptions that you can just rip out hardware or rewrite code to do certain things, or there's always some model that you can go back to. Right? In our case, we may be dealing with code that was written by a contractor that no longer exists, or there's no source code for things, or even any way to figure out what was in a programmer's head at the time a piece of software was written. And so what we've advocated for in all of our research efforts, right, is to not feel limited by this, right? Don't be afraid of it and say it's out of scope to be able to deal with the stuff that we have, but instead let's find power in it, right? How do we think creatively to tackle what really is some really hard challenges, but fun, right? I mean, it's resulted in a lot of great things for us within ONR, both in terms of fresh technical directions. So in terms of getting novel papers and a lot of recognition from that, having productive output in uncrowded areas. Doing research that finds ways to deal with existing systems. Being able to transform a piece of software that already exists, it's already out there. There's a lot of headache in that, but also a lot of power in being able to do that. It allows you to quickly get real-world impact as well. So having tools that are be able to get scalable use across a broad community has been really useful as well. So, so I'm going to ever so briefly hit the wave tops of kind of 3 areas of focus in our program, and then I'll tie them back to how legacy systems, right, our approach to these challenges always goes back to how do you deal with the systems, the code that you have. So one big area for us is resiliency of cyber-physical systems. Right, it's fair to say that computers have permeated almost every aspect of our lives, and one of the big areas that has changed is that we have computers now controlling almost every physical thing in our world. Your car, for instance, is really just a giant computer that you sit inside of and drive around. Modern vehicles have tons of software running inside them. I think Ford has said that the F-150 has over 150 million lines of code running across 100 different processors inside of that vehicle. So it's really staggering the amount of complexity and code and features that are packed into the computing components of things like vehicles and machinery control systems. And so that's really what's important to us, right, is that the security of these systems, right? Many of these computers controlling these really important physical things in our lives were never intended to be interconnected or accessed from the internet. You know, a lot of them don't have many of the luxuries that we've come to find more common in our traditional IT side of things, like, you know, the ability to install patches overnight, or to do incident monitoring, or security scanners, or have a, you know, security operations center or monitor for you know, incidents and problems and security problems. Oftentimes, there's really no way for the users of these systems to even do what we would consider typical cyber defense practices. So in the Navy, we're looking at how do we make these types of systems resilient against attackers, you know, more proactively get after these bugs. And so what we've, you know, the approach we've sort of taken is to come at it from a different angle. A lot of times people see a computer and they want to, you know, get all the bugs out is the idea, right? Achieve cyber perfection. But what we advocate for instead is that we really don't need to accomplish cyber perfection to get what we need out of the security of these systems. Really, to us, a cyber physical system is not just that controller that you see here in the middle of the slide. It's really the entirety of that graphic. It's the physical system, the diesel turbine that's being controlled. It's the sensors and the actuators that act as that interface between the physical world and the cyber world. How collectively can those things be protected, right? If you say that if you're doing CPS security, you really should be thinking about the physics of this system. It's the physics that rules, right? And that's the thing that the user of the system actually cares about, is that, you know, that their system properly maintains control over the physics. And so what we've looked at is integrating new concepts like diversity and into existing fault tolerance, existing redundancies that are already there inside a lot of these systems. And so we're trying to be able to find new ways to make cyber attacks, which normally appear like common mode failures to these types of systems, make the cyber attacks look like, you know, sort of non-deterministic hardware failures that you know, the mechanical engineers are more comfortable being able to deal with and recover. And this approach is really nicely suited to protecting existing systems. There's a lot of flexibility with how you go back into an existing fault tolerance architecture and be able to apply some, you know, diversity across these controllers, right? If all of them are programmed the same, they're all going to get attacked the same by an attack. So that's something that it's a big area for us. Another area that we've looked at a lot is this idea of software complexity and bloat in our code. Right? Modern software is exceedingly complex and bloated. A lot of it ends up looking like these Rube Goldberg machines that you see here on the right, where it takes 20 steps to squeeze the tube of toothpaste. You know, if you looked at, you know, there's a bunch of examples you can find from around the community. We just listed a couple here. One of them that we like in particular is this citation from this was a group at IBM at the time. They were studying the amount of activity that takes place under the hood when you do even just simple operations in software. And one of the examples they called out in the paper was that a stock brokerage benchmark application was executing 268 method calls and creating over 70 new objects just to move a date field from SOAP to Java, right? So just simple, trivial things taking up enormous amounts of activity. You know, this is more going back a longer time here, but even if you look at some things like the true command in Linux. So there's a command in Linux, you can just type true and it returns true. That's really all that this program is ever meant to do. And it actually existed, if you go back into Unix from 1983, it's in there, right? And the size of it is 18 bytes. And over the years, the true command has, you know, been a part of Unix and Linux and all of its various derivatives. And so, you know, looking at some of the more modern distros, and this is from earlier in the decade here, but, you know, 2014 copy of Ubuntu we looked at had over 27,000 bytes to accomplish basically the same thing, like return true. You see this in a lot of the software we use. It's because we're trying to basically maximize code reuse, right? We want it to be easier to implement some new piece of functionality quickly and get it up and get it out to users as quick as possible and sell it to as many people as possible. So all these market practices has really encouraged a lot of growth and complexity and bloat, right? Complexity just sells better in a lot of cases. But from the ONR side, what we've really wanted to do is figure out how can we fight this, right? We know that we can't get programmers to change the way that they write code, and we don't want to redevelop all of the code that we have out there. So we want to work with what we've got. So we've been building a, essentially a software transformation pipeline called late-stage software customization, where we basically can work with binaries, bytecode, things that we have to be able to identify dead code, unnecessary code. Maybe it's developer intended, but user unwanted functionality. How do we actually trim some of that out and better match the code that we execute to the actual deployment contexts that we have, across the Navy and Marine Corps, right? We actually use a lot of common software, but we use it for a very specific purpose. And it would be better if the code that actually runs in our system that's part of that package is just the code that we actually need. In doing this, you find all kinds of benefits, like getting rid of bugs and parts of the code that we never wanted. Thinking back to the Heartbleed vulnerability I talked about earlier, and also just getting more efficient code in the process. That's also really important. And what's really nice is being able to do this approach extends to legacy systems. So working with the software you have again. Another, the last of the three main topics I wanted to highlight is this idea of heterogeneous systems, right? Heterogeneous systems is a term you'll often hear spoken about using other terms as well, like accelerators, domain-specific architectures, software hardware co-design, chiplets. All these types of terms are kind of hinting at the same thing, right? And to give you an idea why this is such a big deal is that the programmer's free lunch is over, right? If you look at single thread performance of general purpose computing, it's been stuck for over a decade and a half. Hardware is really not getting faster. And so if you look at a lot of the systems that we've tried to draw more performance out of over the last decade and a half, we've tried to go to multi-core, so we play that multi-core card. Really, future performance gains, and even the gains that you're seeing now, a lot of them are coming from this idea of domain-specific architectures being used. And the reason this is so important for us is because it is a challenge, right? It's a very interesting technical challenge to be able to, code for this type of system. One analogy to think about is kind of like the idea of remodeling a bathroom and comparing that to a computing task that you want done, right? The way that we've been doing things in computing for years is, basically having a handyman do all of the tasks for us, right? Do the plumbing, do the electricity, do the tile work. And that's been working fine. And multi-core in that analogy is kind of like cramming another handyman into that bathroom. But there's really only so many handymen we can cram in there before we just, don't get any more benefit from that. With domain-specific architectures, what that is basically the equivalent of is having an expert, specialist do all of these, break down the task and have the specialist tackle the right task. So have an electrician do the electrical work, have a tile man do the tile work, right? Have a plumber do the plumbing. And what this gives you is big performance boosts, right? There's orders of magnitude performance boosts to be gained out there if you can actually optimally do this. And, for a lot more information on this, I really would want to point you to, the Turing lecture that Hennessy and Patterson gave from a few years back, titled A Golden Age for Computer Architecture. And it was really a fascinating talk that gets into a lot of the benefits of being able to, make your system take advantage of these expert, computing subsystems. The mobile industry has been doing this for years. If you look at the new A14 chip that just came out for the new Apple mobile devices, it's got, I think it has something like 4 high efficiency cores, 2 high performance cores. There's a, a coprocessor for images. There's a coprocessor for handling the motion computations. There's a 16-core neural engine for doing a lot of new AI machine learning tasks. There's a 4-core GPU for doing graphics and raster computations. Basically, what they've really been able to do is get performance by chunking out all that computation into having very specialized systems on the chip be able to handle it. And the reason that Apple's able to do this a lot is by being one of those vertically integrated companies, right? Vertically integrated companies are finding big opportunities in being able to do this because it's really the challenge is taking that complex task like remodel a bathroom and breaking it out into all those different subtasks and being able to assign those subtasks to that right computing unit is a really big challenge. So we talked about the future of being heterogeneous, but today's code is not, right? How do you take advantage of all of this heterogeneity, these domain-specific architectures, without rewriting the code? Typically the way that they look at it is you rewrite the code and makes use of these specialized libraries. If you've ever done GPU programming, that's the way that it's done in a lot of cases. But really, going forward, our freedom to innovate in the architecture is really going to depend on how can we make that software ecosystem go along with us. And so ONR has been working in this area for the last, let's say, half decade or so as well, anticipating a lot of these problems, right? Because the real challenge to taking advantage of heterogeneous systems is programmability. So one of the areas where we've done some work, and you'll see in the news blurb on the right here, is this system called Popcorn Linux, Popcorn OS, and it's a way to translate all of the C and C++ existing code that we have. How can you, if you can recompile it, how can you have the compiler help you chunk it out, help chunk those tasks out, and figure out how to be able to shift them to the right computing unit at the right time. So really being able to go into the future of hardware systems. So those are three really briefly discussed areas of research within ONR. One of the things we were asked to highlight today was also how you can find out more funding opportunities from the Office of Naval Research. So what I have here is a screenshot of our webpage. If you go to www.onr.navy.mil, you'll see an Explore funding, research funding opportunities link, which is highlighted in the red box there on the slide. You can click that and get more information on various BAAs that we have throughout the year. There's all kinds of programs like STEM programs, YIP programs, MURIs, and small business programs. So definitely keep us in mind when you have great ideas. We want to work with you, and we would love to hear, especially if you have thoughts on how to advance the security of our legacy and existing systems. So with that, start taking questions, and I really appreciate your attention today. Thank you.